We were in the middle of proof. We saw up to here that gamma is defined from gamma initially was defined from H1 in plus H2 to H, and then we made the restriction from N plus to H, and this is a bijective map. And the good thing about this is that now we can transfer the Hilbert space structure of N plus N in perp to H. And more explicitly, for any F and G in H, then we have the inner product of F and G in H. Note that F can be written as F1 plus F2. F1 is in H1, F2 is in H2. The same for G. G1 is in H1. G2 is in H2. And well, we would like to usually to write here that this is the inner product of F1 G1 and F2 G2, but due to non-uniqueness, we cannot do the same, do this here. But now we can do the projection. Consider P to be the projection of H1 plus H2 in N plus and N perp. So, for example, for F1 and F2, which is a pair representing F, possibly this is not the best one, but we can project it and obtain P of F1 and F2. That's possibly another pair, but it's the best one in terms of the definition of norm and inner product. The same for G1 and G2. So G1 and G2 is a pair in H1 plus H2, but we project it and obtain projection of G1 and G2. And the definition here, so definition is the projection of, doesn't matter, any representation, F1 and F2 for F, and the projection of any pair representing G, and this happens in N plus or in H1 plus H2. So that's the way I said we copy the structure of N perp and put it for H. That's precisely what I wrote here. And also the norm, therefore that's the norm of F in H squared is the norm of P, any representation F1 and F2, project and squared. And now we explore the properties of this norm that we defined. First thing, in any space, the norm of the projection on M of X is the same thing as the minimum of all X plus or minus Y when Y is in the orthogonal space. That's very easy and standard. And therefore here I can write norm of F in space H squared, which is defined by definition is P. And note that P is the projection on n perp. Therefore, this is equal to the minimum of F1 and F2 plus any element to its orthogonal complement. So any G and minus G when G is in H1 intersection H2. Here it is. That's a realization of this identity. So norm of projection of something squared is equal to the minimum of the norm of that element plus an arbitrary element of the kernel, the null space, but for all elements in the null space. And you take the minimum. Or if you wish, you can write it this way. So can write it the minimum F1 plus G, F2 minus G. Forgot the square here. For any G in H1 intersection H2. And remember, it's up there. I don't want to go back. F1 and F2 are such that F is equal to F1 plus F2. But when you consider all these combinations, all this F1 plus G and F2 minus G, this is the same as saying that G1 and G2 such that G1 is in H1, G2 is in H2, and the sum is equal to F1 plus F2, which is equal to F. So in other words, our variable, instead of being G, which is in the null space, we move it to the liberty on the choice of G1 and G2, as long as the sum is equal to F. So now I can write it this way and the same minimum. It's just a matter of notation. And in all cases, the norm is in H1 plus H2. And we know that the definition of the norm here is the norm of the first element in H1 plus the norm of the second element in H2 with the same condition. So that is the relation between the norm of F and its representation. The representation which gives the minimal norm is the best one. But now there is a very important observation. And here is the observation. Consider, as before, we write K1, KY1 for the kernel in the first space, and the same for K12, the kernel in the second space. So here is the claim. The elements KY1, KY2, which is in, of course, H1 plus H2, is orthogonal to N all the time for any Y. That's a very important observation. Proof is not that difficult because an arbitrary element of N is like this. Let F minus F be in N, where F is in the intersection. Then what is the inner product of these two elements, F minus F ky1, ky2, that's another element, both element in the space h1 plus h2. By definition, it's the inner product of the first two components. So f and ky1 in the first space plus inner product of the second two elements, which is this one and this one, minus f and ky2 in the second space. And now use the fact that f is in both h1 and h2, and that's the kernel function. So this is f evaluated at point y in the space h1, but it's a complex number fy. And for the second is minus fy, but in the second, it's in h2. But at the end of the day, we have f of y minus f of y, which is 0 for any y. And that is why ky1, ky2, this is orthogonal or to n, or it's an element of n perp. Belongs to n perp. Let's play, that is gonna play an important role now. Now, knowing this, take any f in the space H. So f can be written as f1 plus f2, where f1 is in h1, f2 is in h2. True. What can we say about the inner product of f and ky1 plus ky2 in the space H? You remember the definition above. This is, by definition, is equal to the projection of any representation of f. I take here f1 and f2, and the projection of any representation of the second element. Well, we have a natural choice, ky1 and ky2 in the space h1 plus h2. We had this definition of inner product in H above. And now use the fact that P is a projection. So I can take P to the other side. It becomes P2, but P2 is equal to P. So here I can write F1, F2, K1, K1, 2 in H1 plus H2. I use the fact that P equal to P star equal to P2, and also the fact that P is equal to identity on nperp, because it's a projection on nperp. And that element is in nperp. So these are all used here to remove P. And then we continue. By definition, this is F1 inner product of Ky1 in H1 plus F2 inner product of Ky2 in H2 becomes F1 of y plus F2 of y, which is f of y. So for any y, f of y is equal to f inner product y2 in the space H. So it's more than being a Hilbert space. So it's an RKHS. and its kernel k y in the space H is equal to ky1 plus ky2. Or if you want to evaluate at point X, so k x and y, but for the space H is equal to k x and y in the space 1 or H1. It's k x and y at point H2. This is the same thing as here, but evaluated at X. Or put it simply, k equal to k1 plus k2. So the H that I constructed, it's an RKHS, KHS, with kernel k1 plus k2. Most of this we knew before. The only thing which is rather new here is that the elements of this space are the sum of the element of the first space and the second space. And moreover, now we know how to evaluate the norm of each element. There are some even some nice examples here in the finite dimensional case. But before that, let's have a corollary, which is a useful corollary when the intersection of H1 and H2 is just 0. And that's the easy case. So H1, what happened to me? So H1 and H2 are RKHS on X. And the extra condition here is that H1 intersection H2 is equal to 0. A trivial case. Then H of K1 plus K2 is, well, simply can say the set of all F1 plus F2. F1 is in H1, F2 is in H2. We know this, but moreover, with, in this case, norm of F1 plus F2 in H squared is just normal F1 in H1 squared plus normal F2 in H2 squared, because there is just one representation. It is true that we should take the minimum, but there's just one of them. And well, this also implies that and H1 and H2, because of this representation, are orthogonal subspaces of H. Both of them are in H, but they are orthogonal to each other. It's a special case, but interesting, and you see the only difference is caused by the trivial intersection. Then there is a section about finite dimensional RKHS, which is, an application of this, and what happens. There's nothing delicate in it. I go to the next section, which is for pullback And these consequences for restriction and composition, we will need this when we go to product and tensor product. So pullbacks. Well, assume that X is a set, and we consider a subset of XS. If K from X times X to C is given and is a kernel function, then we may consider the restriction of, let's call it K restricted to S. What can we say about this? Can we claim that Ks is K restricted to S is also positive, which I believe everybody, immediately say yes. It is very natural to consider and to prove, and the proof is not indeed that difficult. So I want to show this, and even I want to go a little bit more, because when I say restriction, it means that I consider the mapping inclusion S from X, I. And then instead of considering K over X, which is indeed over X time X, but we can use this abuse of language. Consider composition of K with I. And then this gives us the restriction over S. I emphasize again that it is true that it's defined over X times X, but you understand, and even in the book, you write it that way. So why just the inclusion? Consider any mapping. So S is not necessarily now a subset of X. So we consider phi defined from S to X, and K is defined from X times X towards C, K positive. And now K composed with phi on S times S with values in C by, again, abuse of notation, it is indeed K composed phi times phi, but you understand what he means, and as I said, even in the book it's written that way. K O phi at point S and T is defined to be a K at point phi S and phi T. So what can we say about K composed with phi? Well, the same thing that we expected for the restriction works for K composed with phi, and here is the proposition. K on phi is bigger than or equal to 0 on S. Proof is easy, but you need to be a little bit careful for the notations and the way you write the proof. So I want to show that this is positive on S. So let S1, S2, S10 be a finite set in S, and alpha 1, alpha 2, alpha n complex numbers. And now what can I say about some I and j from 1 up to n, alpha I bar, alpha j, and k o phi at the point si sj. Well, by definition, this is sum ij from 1 up to n, alpha I bar, alpha j. By definition, this is k evaluated at point si, if at point phi si and phi sj. True. Now, even we usually do indeed, we assume that si up to sn are distinct. So we usually add this, even though it is not needed. But even if we add that s1 up to sn are distinct, phi s1, phi s2 up to phi sn are not necessarily distinct. There might be repetition among them. And that is why I defined this set. AK is the set of all indices I such that phi of Si is xk. What is xk? In other words, I consider the set phi s1, phi s2 up to phi sn. These are elements of x, but probably there are repetition between them. So I can write x1, x2 up to, say, index p, xp. P is not necessarily equal to n. It might be less. And so I put those which create x1 together, those which create x2 together, and so on. So, I mean, you can imagine like this. Here is all phi sj, which creates, I mean, x1, and the same for the last one, which create xp. I mean, I put them in one basket. And what is the advantage of this? Here, I can write it this way. Instead of sum over I and sum over j from 1 to n, I sum over two other indices, sum f over k and l from 1 up to p. And here is sum. I is in ak in one of them, and j is in al. That's why thinking of a partition is important. And k evaluated at point phi si, phi sj. But now, for all I in AK, this is a unique element. This is xk, and this is xl. So, oh, I forgot something. I forgot this. I forgot these coefficients. So I add them here. Alpha I bar, alpha j. True. So what remains is sum k from k and l, both of them from 1 up to p. K xk xl doesn't depend on I and j. So I would have sum I in ak alpha I bar, sum j in l alpha j, k xk xl. And simply call this beta L. So define this to be beta L. This would be beta K bar. So it would be sum K and L from 1 to P, beta K bar, beta L, K, XK, XL. And we know by the properties of K, it's a kernel function. This is positive. And therefore, this implies that K composed with phi is positive. It's not a difficult proof, but I mean, a little bit of attention in the middle. Well, consequence of this, it's an easy theorem, which is called pullback theorem. We have, as before, X and S sets, not necessarily one a subset of the other, but we have a phi which is defined from one of them to the other, from S to X, any function, and K is a kernel on the second one, a kernel. Then we saw above that we can talk about K composed with phi, so we can talk about H of K composed with phi, more theorem. And now we can say, what is this space? Is the space of what you imagine it has to be? F composed with phi, F is in HK, and something similar to what we had before for addition. What is the norm of and for any element, say U in H of K O phi? We have, what is the norm of U in this space? Well, it is natural to say that U is of the form F of phi. Phi doesn't do that much, so it has to be practically the norm of F in H of K. Almost true. Almost true. Here I add U is equal to F composed with phi. So if U is obtained from composition with phi, the norm of U is, I mean, U would like to be the norm of F, but the same problem as before in the case of addition. F is not unique. Different F may compose with phi and give the same function U. And therefore, now it is natural for U, based on what we saw before for addition, to add minimum here. Along all the possible representation, the one which gives the minimum norm is the right norm of U. We have all the ingredients to for the proof. We have developed them before. So assume that F is in H of K. And for simplicity, write the norm of F in HK by the constant C. By the famous theorem 3.1 that we saw several times today, F of X, F of Y bar is controlled by C2 K of X and Y. This is one side of the theorem. And now we can do the composition with phi as we saw before. This implies for every x and y is in x. This immediately implies, based on the proposition we saw before, that f at the point phi of s, f at the point phi of t bar is controlled by C2 K phi of s phi of t for any s and t in S. That's by proposition, which I write as f composed with phi evaluated at S, f composed with phi evaluated at t bar C2, and instead of k at point phi s phi t, I write the kernel k of phi evaluated at point s and t. And one more time, the same theorem that I applied here, it's the same theorem, but from the other way, so it was an equivalent condition. So when I have this, it implies that f of phi is in this space. And moreover, the norm of f of phi in this space is controlled by this constant. In other words, norm of f of phi is less than or equal to all the time the norm of f in h of k, all the time. This is one thing. But I want to show that for any f, if I consider all the possible representation for u and take the minimum, this inequality becomes an identity, an equality. And how can I do that? And to do this, let's L to be the kernel of, instead of K of phi, I write L, it's simpler that way. So L of S and T is K phi S phi T. And so it's the kernel, L is the kernel for the space, kernel of the space H of K composed with phi, or K, H of L. And now, if you consider the U to be a finite sum, alpha I, L, little l at point, say, Ti. Recall that when you have capital L, little l s at point T is L of T and S. That's the convention we had before. So this is a finite linear combination of kernel functions. And for this, we have an advantage. We can calculate the norm of U in the space H of L. Why? Because when we do norm squared, it norm of U and U in the space H of L, it's sum I from 1 to n alpha I L T I sum alpha, well, it doesn't matter which one I, which one J, LTI. And we have seen this many, many times before. So it becomes sum alpha I bar, alpha J, summation over I and J, And L of Tj, inner product with L of Ti, is L of Tj at point Ti, which is L of Ti on Tj. Or the sum I and j from 1 to n, alpha bar, alpha j. This is k, evaluated at point phi Ti and phi Tj. And now we do the same operation backward, but instead of HL, we do it in HK. So if we do this operation backward, we obtain, do this, since time is running, I write the final result. We obtain the norm of the sum I from 1 up to n, alpha I, little k, at point x, this is our x, phi Ti, in HK squared. So briefly, I write the result. If I remove the square, what I showed is that the norm of sum alpha I L, say Ti squared in H of L is equal to the sum alpha I K phi Ti in HK. We can remove the square. We have an isometry. So let me draw a diagram. Here is H of L, which is H of K composed with phi. Mapping here goes to H of L, which is H of K composed with phi. This is our isometry, which I established. I can call it gamma. Goes to H of K. These elements are dense in H of L, so I can extend this from the finite sum to the whole space. So I have an isometry, which goes isometry from H of L to H of K. And here, consider the composition with C of phi. What do I obtain? So if I start with L Ti here, gamma gives me K at the point phi Ti. And when I compose with C phi, note that C phi acts on this element, on this argument. So it gives me K phi Ti phi this. True? Which is the same as L Ti acting. In other words, I obtained the identity here. And this observation help us to obtain the minimum that we had about. So C phi composed with gamma is the identity on H of L. H of K composed with phi. And therefore, for any U, here is for any U in K in H of L, there is an F among all the representation. You consider a U here. Oh, what's happened? You consider a U here. A U here. But U can be here too in the space. So U goes to an element F here, and then compose it with phi gives you the same U that we started with. So U can be written as F composed with phi, where F is gamma of U. The good thing about this specific representation is that norm of F is equal to the norm of U. This is in HK, this is in HL. So we obtain one representation for which the equality works. Go back here, go back here. All the time, norm of U is less than or equal to the norm of F, but there is one specific representation for which the identity holds. And that is why I can write norm of U is equal to the minimum of all possible representation of all F such that U is equal to F composed with phi. That's the end of the story. Well, it's a good time to stop here. Sorry, I went a little bit over time.